Good morning, everybody, and welcome to our last unit in this class. You can see we are talking about exponential functions. Ignore the fact that that's labeled as 4.3. I've taught this in a different order this semester. So with this particular set, there's going to be a lot of calculated work with Desmos, and we'll be going back and forth. But we just want to understand what makes a exponential function an exponential function. Whenever we talk about exponential functions, we are talking about a function that has some base value and its exponent contains the variable. So that's where we come up with what a true exponential function is. During this particular moment in history, we have talked about exponential functions a lot. You've heard it on the news. You've heard about flattening the curve. You've probably heard about logistic growth, but exponential growth is what we're talking about, or exponential decay for today's notes. So example 1 is just something really straightforward. It just says to evaluate these particular values using a calculator. So we're going to go into Desmos, and I'm just going to type these in using the calculator. So we have 2 raised to the 1.4 power. That's part A. For part B, it's 2 raised to the 1.41 power. I'm going to type that one in. Part C. Part D. And then finally part E. Pull up the square root here. All right, so we cycle through these, and you can see we started out at 1.4. We get 2.63. 1.41 is 2.66. 2.1414, 2.665. And these values are all trending towards the actual evaluation of 2 radical 2. And so we're just looking at approximations for the first 4 parts of that. We've taken the square root of 2 and approximated it to 1 decimal place by using the 1.4, 2 decimal places, 3, 4, and then finally the exact value of square root of 2. And that just kind of shows you how these different approximations will have an effect on the overall value of an exponential function. So really nothing too brain busting there with those evaluations. So some of the laws of exponents. Now these should be things that you are very familiar with already at this point. You've seen it in Algebra 2. If you've taken pre-cal, I think there was a couple of you that may have said you've taken pre-cal, so you would have seen it in there. And you've definitely seen it on the ACT. The first one that you have right here, when we have the same base and they have different exponents, well, the way we can simplify that is we can write it as that base raised to the sum of the 2 exponents. For a power raised to a power, you just multiply the 2 exponents together. There is a distributive property of exponents where if we have some quantity raised to a power, each individual value within that quantity gets raised to that power. 1 raised to any power is still going to be 1. If you have a negative power, you can write it as 1 over a to the positive exponent, or you can just write it as 1 over a quantity to the positive exponent. And this says a to the 0 equals 0. That is wrong. I don't know why I typed that in there that way. A to the 0 is always equal to 1. Anything raised to the 0 power is going to be 1. So here we talk about exponential growth. Kind of a little quick introduction. And so suppose that you have a function that has the following properties. 1, the value of the function doubles for every unit of increase across the x-axis. And then the value of f at x equals 0 is 5. So we have some initial conditions. The first one being that when x is 0, the value is 5. And we know that for every unit increase of x, f of x doubles. So that's why you see we have this column 1, 2, 3, 4 for x. Every time x goes up by 1, the value for the function doubles. So 5, 10, 20, 40, 80. And if we wanted to try to find an equation for that, we've taken the values in the second column. They're listed right here, 5, 10, 20, 40, 80. And we see that if we double the previous value, we get the second value. If we double that value, we get the third. We double the third value, we get the fourth. We double the fourth value, we get the fifth, and so on. And we kind of expanded these out over here to the right. So the first value is simply just 5. The second one is 2 times 5. The third one is 2 times 2 times 5. The fourth one is 2 times 2 times 2 times 5. And then the fifth one is 2 times 2 times 2 times 2 times 5. And we can simplify that and note that these x values correspond to our exponents now. And so we've come up with a general equation or a general form for this particular function. And it's going to be 5 times 2 to the x power. 5 is important because that is our initial value. And then the value for where we have the 2, that's indicating that this function is doubling each time. And then x is just our exponent. And so that gives us the definition of an exponential function. And you can see that here in the green box in the middle of the screen. C times a to the x. C is your initial value. That's the initial condition, whatever you started with when x is 0. A is what it's your growth factor. That could be an integer value. It could be a decimal value. Whatever the case might be, that's going to be a. So if back at the previous example, our initial value for the function was 5, and we were doubling, so it means we were multiplying by 2. That was our growth factor, and that's how we came up with the equation 5 times 2 to the x. Some examples of exponential functions are illustrated right here. Anything that has the variable in the exponent will be considered exponential. And one thing that we can note now, going on into example 2, is we can kind of use the information that we just obtained from that last little where we did the 5 times 2 to the x power, and we can generate a function based off just a model, some data that we're given. So the first thing we want to do in all three of these examples is determine whether it's linear, exponential, or neither. If it's linear, we find the model. If it's exponential, we find the model. If it's neither, then we don't have to worry about it. Apparently I had a rough time typing these up because that should be part C. All right, so let's look at part A. The first thing you want to do in any case here is you want to look at the difference between successive values in the y column. So here we notice that from 5 to 2 we decrease by 3. From 2 to negative 1 we decrease by 3. From negative 1 to negative 4 we decrease by 3. Negative 4 to negative 7 we decrease by 3. So the change in y is constant. And we notice too that our change in x is also constant. X is going up by 1 every time. Y is decreasing by negative 3 every time. So when we have a constant difference in our y values, we know it is a linear function. And linear functions are always y equals mx plus b. M is our slope, which we have found to be negative 3. B is our y-intercept. Well, our y-intercept occurs when x is 0. So we have all that. And we can write out our formula. Y equals negative 3x plus 2. So we didn't have to do a whole lot of calculations there. We can just look at the table and come up with the solution. For part B, we're going to do the same thing. Let's compare our y values. So we reduced by 16. But here we reduced it by 8. Here we reduced it by 4. And here we reduced it by 2. Well, what that tells us is, one, this is clearly not a linear function because the change in y is not constant. So what we have to do next is do a ratio of the differences through the y value. So here we would take negative 16 divided by negative 8, and we get positive 2. We would take, well, let's not do positive. Let's do it this way. Let's do 8 over 16, rather. Negative 8 over negative 16 was positive 1/2. Negative 4 over negative 8 is positive 1/2. Negative 2 over negative 4 is positive 1/2. So a ratio of the differences gives us this value of 1/2. When we see that, we know that it is exponential. And remember from our formula before, it's c times a to the x, where c is your initial condition when x is 0. So we have c is equal to 16. A is our difference here, our ratio, which is 1/2. So we can write out our function now as f of x equals 16 times 1/2 to the x power. And then finally for part C, we do the same thing again. Difference is 2, difference is 3, difference is 4, difference is 5. And then when we do a ratio of the differences, we get 3/2, 4/3, 5/4. Well, we notice there too that a ratio of the differences is not a constant value either. So this is neither linear nor exponential. So we don't have to do any more work on example 2. So you're just looking for if the difference is constant between the y values, then it's linear. If the difference or if the ratio of the differences is constant, then it's exponential. Otherwise, it is neither linear nor exponential. Sorry, I gotta drink my coffee. All right, example 3. Graph the exponential function f of x equals 2 to the x power. So let's go to Desmos. Let me clear these out of here. So we're graphing 2 to the x power. And you can see that the Desmos gives you that graph. We do have one critical value at 0, 1. That's important to note because exponential functions will always cross the y-axis at 1. So we can go ahead and just kind of transfer this graph over. We have a y-intercept at 0, 1. And there is our function. That's the graph of that exponential function. So you can see these aren't that difficult to do, especially with a calculator. What we want to pay attention to, though, is the base. So on this one, the base is 2. I'll come back and talk about what's here in the red box in just a second because we're going to look at another example real quick with example 4. This one, we're graphing 1/2 to the x power. So I'm going to graph that on the same axis as 2 to the x. I'm just going to type that in as 0.5 so I don't have to bring up a fraction. So 0.5x, you can see that's the blue graph. It crosses the same point on the y-axis, but in this case the function is decreasing. It is not increasing. So let me make a note of this. If I can draw this, that's pretty good. Okay, so there's that function. Now what we're looking at, if I can zoom these out enough, you can see the 2 to the x there at the top and then 1/2 to the x at the bottom. The only difference between these two as far as the expressions go is one has that integer value of 2 as its base. The other one has the integer value or the decimal value of 1/2 as its base. And that's going to lead to these two red boxes under each one of the examples. The domain for both of them is all real numbers. The range is going to be the set of positive real numbers. They both lie completely above the x-axis. Has no x-intercept because it never crosses the x-axis. And they both have a y-intercept of 1. In both cases, the x-intercept or the x-axis is a horizontal asymptote. The difference between the two is right here with number 4. Is if a is greater than 1, so that's our base value. So in this first graph, the base was 2. It is an increasing function. If that base is less than 1, if it's between 0 and 1, then it's going to be a decreasing function. and that's what we note here in this second example, and that's right here with note number 4. When the base is between 0 and 1, it's a decreasing function. It represents exponential decay. Anytime that a is greater than 1, we have exponential growth. Here with example 5, we're asked to graph 2 to the negative x minus 3. So again, we'll go back to Desmos. I'm going to clear these off now. So this is going to be 2 to the negative x. Let's see, was that minus 3 in the exponent? No. Okay. So 2 to the negative x minus 3. And here's our graph. So we note now that it has shifted this entire function down 1 unit, or 2 units rather. Sorry, 3 units. Because our original y-intercept was at 1. Our new y-intercept is at negative 2. The crinkling you hear in the background is Steven getting a bowl of cereal. Whoops, hit the wrong thing. So when we graph this, we have a y-intercept at negative 2. And our graph now looks like this. That's horrendous, but it's pretty close. So what we've done is we've just taken that graph of 1/2 to the x power from example 4, and we've shifted it down 3 units. That's why our y-intercept has dropped down to negative 2. It's gone from positive 1 to negative 2. We've shifted it down 3 units. And the horizontal asymptote is going to be right here at y equals negative 3. And that's just based on the simple fact that we've shifted the entire graph down 3 units. So the horizontal asymptote comes down from 0 to negative 3. The x-intercept comes down from 1 to negative 2. And the graph still retains the same shape. Just it's in a different spatial location within the coordinate plane. The number e, you may have seen this before. You've probably heard me talk about it. It is referred to as Euler's constant. It's an irrational number, much like pi. There's a couple of different ways to express the value for e. You can see the first example here is 1 plus 1 over n raised to the nth power. And then as n approaches infinity, we can apply calculus to that, and we can use what's called a limit. And that gives us a more exact value for e. But for now, just understand, though, that it's just like pi. There's no real true way to compute pi other than knowing that it's the ratio of the circumference to the diameter. Whereas with e, you have to use calculus to come up with the exact value. So typically we will see decimal approximations of e, much like we would with pi. This table provides different values showing you how we can approach e. The larger n gets, you can see that in the first column. The fourth column shows the exact value of 1 plus 1 over n to the nth power. It gets closer and closer to the true value of e, which, as I stated before, is irrational, so it would go on forever. Example 6, graph the function, determine the domain, range, and horizontal asymptote. So we're going to graph negative e raised to the x minus 3 power. We have negative e raised to the x minus 3 power. And I did not put that negative 3 in the exponent. There, nope, still not getting it. Try this. Better. Okay, so there's our graph. You can see that it does not approach the or it doesn't cross the x-axis. The graph is flipped from what e to the x would look like because of that negative in front. And we can graph this on our notes. It's going to look something similar to this. And so for the domain, remember the domain is all the x values. So from left to right, that's going to be all real numbers. We can put in any x value and generate a y value in the domain. For the range, we're looking at the y values, and that's going to be all the negative real numbers, or everything less than 0. So it's going to be all y such that y is less than 0. This graph actually never makes it to 0. And then the horizontal asymptote will be the x-axis, where x is equal to 0, or y is equal to 0 rather. Solving exponential equations is something that's very simple to do. It just takes a little practice. You're going to have to look for ways to write these functions with similar bases without having the same base. It makes them very difficult to solve. So the first one we have is on part A, we have 3 to the x plus 1 is equal to 81. We want to solve that for x. Well, what's nice about this is we know that we can rewrite 81 as a base 3 number. 3 to the fourth power is going to be 81. So because these two functions have the same base now, we can just simply set their two exponents equal to one another, because the only way that the left side and the right side can be true is if their exponents are equal. So we'd subtract 1 from both sides, and we get that x is equal to 3. Part B, same thing. What we need to do now, though, is we note that we can't write 8 as a base 4 exponent, and we can't write 4 as a base 8 exponent, so we have to come up with something else. Well, in both cases, these can both be written as a base 2 exponent. And then we raise them to their original exponents here. So one of our notes from the exponent, or the rules of exponents, is when you raise a power to a power, you multiply them together. So here I get 2 to the 4x minus 2 is equal to the 3x plus 9. So just like in part A, now that we have the same base, we just simply set the exponents equal to one another, and we solve for x. So I'm going to subtract 3x from both sides, so that gives me x minus 2 is equal to 9. Add 2 to both sides, and I get x is equal to 11. Example 8. Same thing, we have to apply the rules of exponents to solve this, but it's going to take a little bit more creativity perhaps to come up with it. The left side we're going to leave unchanged for right now. It's negative x squared. This first term, e to the x to the second, remember power raised to a power you multiply, so that's e to the 2x. And this second term on the right hand side, it's 1 over e to the positive third. Well, if you look back at our exponent rules, that is also the same as e to the negative third. So we can write it that way. So now we have everything across the board in terms of base e. Again, I'm going to leave the left side alone. E to the 2x times e to the negative third. You multiply like bases. You add their exponents together. And now I'm back to exactly what we saw in example 7. I have the same base on the left and the right, so I can equate their exponents. So I have negative x squared equals 2x minus 3, and I can solve for x. In this case, I'm going to add x squared to both sides. And now I have something that I can factor. This is x plus 1. Or sorry. That's a minus 3, not a plus 3. We're going to have x plus 3, x minus 1. And when I set those factors equal to 0, I get negative 3 and positive 1. And then finally with example 9, we're going to kind of do an applied problem here. Again, nothing that you can't really accomplish without the calculator. But we're talking about between 9 p.m. and 10 p.m. cars arrive at Circle T at the rate of 12 cars per hour, which is 0.2 cars per minute. The following formula can be used to determine the probability that a car will arrive within t minutes of 9 p.m. For part A, determine the probability that a car will arrive within 5 minutes of 9 p.m. So that's just a matter of taking the given function and evaluating it at 5. So you get 1 minus e to the negative 0.2, and then we replace t with 5. And then when we type that in on our calculator, sorry, I don't remember what I was saying. Somebody decided to come in and get some ice while I was doing this. We're evaluating the function at 5 for part A. So all it is, we just simply type in 1 minus e, and then our exponent is negative 0.2 times 5. So I'm going to put that in parentheses, negative 0.2 times 5. And we get 0.6321. That's what we're going to go with. 0.6321 is our value. All right, and so if we change that to a percentage, that is 63.2%. So there's a 63.2% chance that within 5 minutes of 9 p.m., so anywhere from 9 to 9:05, there will be cars arriving in the parking lot at Circle T. For part B, now it's saying what's the probability that a car will arrive within 30 minutes of 9 p.m. So in this case, we're looking at f of 30. We replace t with 30. And we're going to type that in on our calculator. So I'm going to go back over here. And what's nice about Desmos is I can just go right back up here, change that 5 to a 30, or 309 for that matter. There we go, 30. And I get 0.9975. And that is going to be approximately 99.75%. So between 9 and 9:30, there's a 99.75% chance that there will be at least one car show up at the Circle T. Part C, we just want to graph the function. So I'm not going to sketch the graph on the notes here. I'm just going to go ahead and type this function in. 1 minus e negative 0.2x. Okay, and you can see here on the screen what our graph looks like, and we can keep zooming out. What you'll notice is that I'm going to graph y equals 1. We have a horizontal asymptote at 1, and that's going to be the answer to part D, and I'm going to show you how to do that without actually having to graph this. It's just a matter of kind of thinking it through. So part C, I'm just going to put calculator. For part D, if we're taking 1 minus e to the negative 0.2 t, as we can rewrite that as 1 over e to the positive 0.2 t. So as t gets really, really big, okay, we're talking about as t goes to infinity, that denominator gets very large as well. Even though we're multiplying it by 0.2, it's still going to increase in size. So 1 divided by an infinitely large number approaches 0. So this whole term right here approaches 0, and all we're left with is 1. So we essentially have 1 minus 0, which is going to be equal to 1. And that's what our function approaches. And that makes sense because we can't have more than 100% of anything. And if this surpassed 1, then we would be implying that there is a greater than 100% chance of the Circle T parking lot having cars in it. And we know that that is a mathematical impossibility. This also, part D, kind of goes back to a little bit of calculus as well. Again, we're talking about limits and evaluating something as a variable approaches some other value. In this case, t approaches infinity. And we can see then that the whole function itself only approaches 1 at most. That is the conclusion of this set of notes. Take a look at the suggested problems, and I'll be releasing our next video tomorrow.